All right, how's it going, people? Welcome to the office hour with Dr. Alberto Cruz. Today's topic is the minimum function. So at this point, we're kind of familiar with the stack, and we have experienced a little bit about what calling conventions are for, as well as the concept of saving the return address in the stack. And that's going to come into play today, as we will override the definition of a minimum function to have various versions of the minimum function that take a varying number of parameters, and all these various minimum functions will call a binary minimum function that you see here. So let's take a look at the function prototype for this. So this is an integer function, min, which will take two integers and it will return the lesser integer. So for example, if a is greater than b, it'll return b. If that's false, it will then return A. So focus on the function prototype here and remember the previous videos and how the calling convention works with ARMv8. All right. So if you're looking at this, the function prototype should be passed the parameters in a left to right order. So the integer A would be passed in the register W0, and the integer B would be passed in the register W1. It does return an integer, and you only return one value. Note that we will return the value through x0, which just happens to be also, being used as an incoming register. That is a weird sort of thing to note with ARM, is that the same register is used for in and out, basically. But anyways, from the perspective of the callee, that's not really our problem. Main will set that stuff up for us, and it'll just work out. So let's take a look at another version of this function that uses three inputs. So when you're interpreting this function, just assume that that previous version still exists and would be in the same linked binary. So here we have a minimum function. The main difference here, it has a third input, so this is a ternary function, and it returns what? It gets away with calling that binary implementation of the min function, assuming it works. Basically, what'll happen is it'll return the minimum of B or C, and then whichever one is less would then be passed to the minimum, a second call to minimum of A, and whatever that first function call to minimum would return. All right. Let's go ahead and take a look at a main function that would potentially interact with these. All right, let's have a look at our main function. What you can see is it's a pretty simple main function. Of course, we want to include stdio so that we have the ability to use a printf. Then we have our function prototypes for min, both the binary and ternary version. Note here that I'm actually appending like a number for the number of arguments for it, so we don't have to handle the function overloading problem at the assembly level, which might be a little weird at this point. Choosing to not actually dive into that, and then in the main function, it's pretty simple. We just have a printf. It has a string literal with a token %d/n. So the %d means insert an integer here, a single integer. /n is the escape character to cause a new line when printing out to the screen. The second argument to the printf is the list of arguments in order. We only have one, right? Actually, min3 is actually returning only a single argument, and whatever integer it returns would be placed in that %d, all right? And we'd expect min3 to return the minimum of the numbers 1, 2, and 3, so this program should really just be printing 1, all right? So our next step is to implement min2 at the assembly level. So I have my editor again. Let's go ahead and code this thing. We want a global function called min2. We will start coding it. At this point, this is when you would create the stack frame for your function. But this is a leaf function. What does that mean? That means that it is not calling any other functions. So it doesn't really need the stack to save the return address or anything like that. In fact, if we think about what the code should be doing, it should be doing the following. It should be doing if A is less than B to return A. Otherwise, the concept is to return B. So actually, for this leaf function, actually, it turns out that there's no local variables. There's no subsequent function calls within this, so we probably don't need any stack space at all. If we code this thing efficiently, we'll get away with not even messing with the stack. So basically, at the end, we could just call ret because we're not going to make any function calls within this min2 function, okay? And we should be okay too, so long as we stick to using registers for our work that are identified as scratch registers or caller saved, basically. And those would be the input registers are unsaved, meaning we can mess with them as much as we want, as well as the temporary registers X9 through X15. Okay. And if you stick with those, then you don't need the stack. But if you were to use literally any other register, you'd have to make it. You'd have to allocate stack frame space. Okay, so if you're looking at this, the function prototype int min2, int a, int b, that sort of thing. We expect the first argument in W0 and the second argument in W1, right? W again because they're 32 bits. Let's just leave them there and not mess with them so that we can use it as a reference point for our code. If we ever need, scratch registers, I guess we'll see. Do we even need scratch registers for that? Let's see. So, all right. So, basically, the idea is if A is less than B, so we want to compare first argument A against the second argument B, right? Because it was in left to right order. If that was correct, if branch, if less than, then we want to return A, basically. So what I've done here is I've made the if block the jump target. That means the fall through slot will be the else. So if you end up down here, actually, this is the concept of the else after this BLT, you then return B. All right. How do you return B? Well, the caller will expect the result in the W0 register. All right. So all we have to do is move the value of B, which is int B, into the register. So these two commands may look similar, but actually this one here is a little different. It's actually moving the value of W1 into the register W0. So that basically moves the concept of B into W0, which is the return register. So this instruction right here can literally be interpreted as your concept of return the value of B. All right. And then we will have RET to just leave the function. All right. We haven't implemented return A, so let's go ahead and do that. So it's return A. What should that do? So actually, hey, wait a minute. Let's think about this. So if we need to return A, what do we need to do? We need to take the value of A and place it into the return register. The value of A is in which register? It's already in W0. So even if you were to implement this, you would be moving the value of W0 into W0. Actually, W0 is already in W0, basically. So actually what we could do is just make this point return A. All right, now this looks a little weird. Okay, I don't blame you if it looks a little weird, because if you're thinking about this in terms of a high-level language, basically, I said that the stuff below the BLT was the else block, but I want to point out that the label, you can fall through on a label, right? The only way to make it a proper block would have been if you did something like this, J to some other label or something like that, but that's not there. So basically what will happen is the logic for returning B, that block that returns B, falls through into here onto the return. Note that it is still slightly different because it modified the contents of W0 before approaching the return, whereas if you just jump directly to return A, it would contain the value of A in W0. All right? Okay, let's check out the ternary version of this, let's code it up in a separate assembly file. All right, so min3 is going to be the challenging one. We can start coding, I guess, but we probably are going to need to write the pseudocode down to get this one right. So min3 is a function, and what it looks like at the C level is this. We have int min3. We have 3 inputs, int A, int B, int C, and it has a very much a compound statement, which is you return the first call to you return the second call of min, where the arguments are a, comma, a first call to min. And I say first, I ordered them, I said the left one, this one here, I called it second and this one first, because if you're looking at it, you actually have to apply the inner one first. And you're basically returning this thing. All right, as far as the input arguments go, that one's pretty straightforward. This is W0, this will be W1, this will be W2. This thing, we actually have to unpack into a sequence of steps, right? At the C level, it looks so elegant. You think, oh, I just have a single return statement. No, that's not how it works. you gotta part this thing out into basically atomic operations that would be carried out by our microprocessor. What are those operations? So I think we're gonna have to get some sort of temporary register to be equal to min of BC. So we'll end up calling min BC once, and then we'll have a second temp to min, and this is min2, by the way. So these are calls to min2 that we had previously implemented. Min2 of A and temp this time, noting that this would have got the minimum value of B and C and stored it in temp. So here the result of this should be the minimum value of A, B, and C. All right. And then finally, you would end up returning that value of temp2. Some concerns before we start coding this thing. This function is a non-leaf call. What does that mean? That means that we're going to need to save the return address. On top of that, these temporary variables right here, temporary variables are lost on a function call. So it's possible that we would need to have at least some stack space to store the intermediate result of temp. So I guess to allocate stack space for ourselves, we'll subtract a value from the stack pointer. This is the point in class where I'm going to ask you what your favorite number is. Let's go with 16, I guess, in the absence of any other number. If we need more space, we'll allocate more. And the first thing we're going to do is store the return address at the bottom of our stack frame, all right? And then to add some code for closing out the function, what we're going to do is first you load x30 sp, right? You reset the stack, the return address from the stack. You then pop the stack by reverting the stack pointer to where it was previously. You do that by just moving it up by the same amount of space that you moved it by, and then a return call, noting that this return call would actually use the value of x30 that you had restored from the stack. So by doing this mechanic where you open min3 with this and close it with this, it would actually return from main, resolving that foobar example from a couple videos ago. All right. Okay, so let's code this thing up. Let's see here. So we need to call min2 of B and C. All right. So what does that mean? So that means that from this perspective, actually, we're the caller. So that means that we have to place the value of B in W0, and we have to place the value of C in W1. All right. So let me just point out here. So if I move the value of B into W0, on entry, we had A placed in W0. right? What does that mean for our second call? This, like if we called into min2, or if we called min2, input argument registers are not saved, meaning we can't expect them to be the same value on the return. We would have lost A forever. So actually, indeed, we're going to need some temporary variables. Or rather, the proper term for this is if those variables are local variables that were passed as input arguments, we call that a shadow copy. So I'm going to do this. I'm going to just write out the code, and then we're going to discuss what the boundaries would be for this. All right, so basically this starts at SP plus 0, all right, and goes all the way to 7, basically, all right, because it is 8 bytes, because it's an X-sized register. So that means if I want to place this below it, W0, oh, hold on, these would be for the other inputs. If I want to place W0 just above that on the stack, that means the next free space is 8. This is a W-sized register. That's 8, 9, 10, basically. Or wait a minute, I can't add. It's 8, 9, 10, 11. All right, right. That should be 4 bytes, right? The reason why we're doing this is so that we know exactly where to start the save position on the stack, so that we don't end up clobbering it. You could easily make a mistake here, where like, hey, maybe I forgot that an X register was if you forgot maybe an X register occupies 8 bytes, and then you attempt to store W0 on the stack with an offset of 4, you would actually cause it to occupy space that had the original version of the return address, and you'd end up destroying that return address, all right? And if you understood that, then I'm just going to go ahead and move forward here. Remember, we got to revert this thing to 8, because that's actually the next free space on the stack. But these following variables are all units of 4, so you can actually just add 4 to that, like 12 and 16, to place them properly on the stack so they don't end up colliding with each other. All right. So that is our concept of shadow copy. That is, this instance of min3 will preserve the input arguments as you have called it. So we can now call these other functions, such as min2, without any worry of losing the values as the function was called. All right. Okay, so what was the goal here? The goal was to load the value of B into W0 and load the value of C into W1. I'm going to do it the maybe expensive way, and then we're going to discuss a potential optimization here. So if I want to get the value of B, I had just placed it on the stack. So actually I could load the concept of B into W0. Let's actually change our notes here to from like stack positions to what these variables are. This one was integer A, right? Thankfully, it was in left to right order, and I loaded them onto the stack in a logical order. So we know that this first one, basically SP8 is A, SP12 is B, and SP16 is C. So if we wanted to load the value of B into W0, we'd issue an LDR command and get that from the stack SP12, basically. So that means get our shadow copied value of B on the stack, dereference its position, and place the value into W0. Do the same thing for C, all right? But in this situation, C is actually SP16, all right? Okay, so there you have it. Though I want to point out here that basically if you end up at this instruction, we technically have not modified the values of W0, W1, and W2 at all. All right. So if you arrive at that point, the value of B should still be in W1, and the value of C should still be in W2. So if you wanted to have maybe a quicker optimization here, you could do a move command to move these registers like so. And remember, it's right to left. So what this will do is this will shift the value of B, because the value of B still exists in W1, and it'll put that in W0. And the value of W2 will be shifted into W1. And then we will call branch and link min2. All right. Okay, so that will then call min2. And what we should expect is that the register X0 should contain the result of min of W1 and W0 and W1. However, because this was a function call, make no assumptions about the order of the registers. I know that we coded it, so I know there might be some sort of impulse on your end to actually try to assume what happened with the registers. Don't do it, okay? That would lead to bad habits. Just always assume that after a function call, that the input arguments will no longer be the same, or any scratch registers would be the same, okay? So what does that mean? So that means that you can really only, and actually, by the way, this would be a W0, it wouldn't be an X0, right? Because it's 32-bit value. So anyways, that was a digression. Going back to our main thought here, um, what does that mean for us? The only thing that we can be certain of is that the value of W0 should contain the minimum of the two input arguments we sent it, basically. That means that this actually, in our current notation, would be temp, basically. The concept of temp or W0 currently here, all right? All right, so now what? We need to perform a second call to min, this time, or we need to perform a second call to min2, but this time what we need to do is we need to place A, which honestly, we're going to have to use the stack for that one, right? Because based on what I said, after this call, you can't assume that W0 is still there. In fact, it's not. We totally destroyed it. This second value, temp, we have it. We basically have it already. There's no need to copy it onto the stack, because basically this is the most immediate thing we're going to do. We're not going to call any other functions. We've got our value, and that's the value you need. Just push it into that function and don't worry about losing it, basically. Just go with it. So this would already be contained in W0. So what we need to do now is, I guess the first thing we'll probably want to do is to move. This note means that this is where it currently is. However, we need that value on the stack to be in W0, and we need whatever is currently in W0 to be in W1. I think I'm going to move W0 into W1 first, and then take the value from the stack and have it clobber W0. All right, so that we don't lose temp. Basically, that's what we're trying to do here. So we'll move into W1 the value that's currently in W0, and then we will load from the stack into the register W0 the value of A, which is SP8. So if you look up here, indeed the original version of A was located at SP8, and then we will make a call to min2. Okay. At this point, I want to point out that the result of min2 would be would actually be this thing. All right. The idea that whatever min2 returns in W0 would be considered as temp2. The idea that there was a call to min2 and it returned the minimum of both of these arguments, and it would have placed it in W0. So actually, we need to return temp2, but through the course of whatever the calling convention was, it's already contained in W0, so we don't need to perform any other actions at this point. All right, we can just return. And just a couple of notes here before you attempt to compile it. You're going to want to delete these comments. These were helpful for explaining stuff, but generally speaking, the assembler does not like comments at the ends of lines, at least if you're using a hashtag. All right, so make sure to delete these comments at the top if you're actually following along in your environment. All right, let's compile this stuff. So we haven't compiled anything at this point, so we'll run gcc flag warning all, no optimizations. We will want the output to be an unlinked binary. We want the output to be main.o, and we want to compile main.c into an unlinked binary. All right, good deal, no errors. We want to do the same thing for min2.o, except this time min2 is in a .s file. All right. Cool. No errors. All right. Now that was the easy one there. Just a couple of lines. Min3 was the weird one. All right. Let's change a couple of characters here. All right. Cool. All right. Now time to link it together, I guess. Same commands. Note this time the -c command is only when you want an unlinked binary. In this case, we want a linked single executable file. So definitely do not use -c here. You want the output to be main.out. We want to pass it all of the .o files that we previously compiled. That would be main.o, min2.o, min3.o. All right, cross your fingers. Oh, typo. Whoops. All right, there we go. All right, well, I mean, there had to be an error. I'm calling GCC 4 times. It'd be weird if there wasn't an error. Okay. All right. Let's just run this thing just to see if it works. So remember, we called min3 with 1, 2, and 3. The minimum value of 1, 2, and 3 is 1. If this thing works, we should see a value of 1. All right, cool. Worked on the first try. Cool. All right, so that's it for today, people. In the future, what we're going to do, we're going to implement a recursive factorial and then a recursive Fibonacci. Have a great day, everybody.